In the depths of space, beyond the countless stars and swirling galaxies, lies a question that challenges the foundations of human understanding. How can something be infinite and yet possess an edge? Our everyday experience tells us these ideas are mutually exclusive. Infinity suggests endlessness, a boundless expanse without limit. An edge implies a boundary, a place where something ends and perhaps where nothing begins. Yet some modern cosmological models propose that the universe we inhabit might somehow embody both qualities at once. As we peer deeper into space and decode the ancient light that has traveled billions of years to reach us, we confront a truth that defies intuition. The universe may be governed by rules our evolutionary heritage never prepared us to grasp. When astronomers speak of the universe, they're actually talking about two distinct concepts that often get conflated in popular discussion. There's the observable universe, and then there's the entire universe. And the difference between these two is not just enormous, but potentially infinite. The observable universe is everything we can see, have seen, or could ever possibly see, even with perfect instruments and infinite time. It's bounded not by some physical wall or barrier in space, but by the fundamental limitations imposed by the speed of light and the age of the universe. Light, despite being the fastest phenomenon we know, travels at a finite speed of approximately 299,792 kilometers per second. This speed, while incredibly fast by human standards, becomes almost frustratingly slow when dealing with cosmic distances. The universe itself is approximately 13.8 billion years old, born in the violent explosion we call the Big Bang. You might think this means we can see objects up to 13.8 billion light-years away in any direction, giving us an observable universe with a radius of 13.8 billion light-years. But the universe has been playing a trick on us, one that involves the very fabric of space itself expanding. While those ancient photons have been traveling toward us for 13.8 billion years, the space between us and their point of origin has been stretching, expanding, carrying those distant objects ever farther away. By the time that ancient light reaches our telescopes, those distant galaxies are now roughly 46.5 billion light-years away in any direction. This gives us an observable universe approximately 93 billion light-years across, a sphere of visibility centered on Earth. Not because we occupy some special position, but simply because that's where we happen to be making observations. But here's the crucial point. This observable universe, this sphere of everything we can possibly detect, is very likely just a tiny fraction of the entire universe. Beyond that horizon, beyond the reach of even the most ancient light, the universe almost certainly continues, potentially forever. To understand how we ended up with this cosmic horizon, we need to journey back to the very first moments after the Big Bang, to a period that lasted less than a trillionth of a trillionth of a trillionth of a second, but which shaped the entire cosmos. This epoch, called cosmic inflation, represents one of the most dramatic events in the history of physics. During inflation, the universe didn't just expand, it exploded outward at a rate that vastly exceeded the speed of light. This doesn't violate Einstein's relativity because nothing was moving through space faster than light. Rather, space itself was expanding, stretching, growing exponentially with each infinitesimal fraction of a second. In a time interval so brief that it defies human comprehension, the universe grew from something smaller than a subatomic particle to something perhaps as large as a grapefruit, or perhaps much larger. But here's where it gets truly mind-bending. Even as a tiny region inflated to cosmic proportions, other regions inflated as well. regions that began the process slightly out of sync with ours, or which inflated at slightly different rates, or which stopped inflating at different times. This means there are vast tracts of space, potentially infinite tracts, that were part of the same primordial quantum fluctuation as our observable universe, but which have been carried so far away by the momentum of inflation that we will never, ever be able to see them. The light from these regions is still traveling toward us, racing through space at its maximum speed, but the space between us and them is expanding faster than the light can traverse it. It's like trying to swim to shore while the current carries you backward faster than you can swim forward. These regions represent a kind of edge, not to the universe itself, but to the portion of the universe that we can ever hope to interact with or observe. They create a boundary defined not by any physical barrier, but by the fundamental geometry of spacetime and the history of cosmic expansion. The shape of the universe itself offers another perspective on this paradox of infinity and boundaries. When cosmologists talk about the geometry of space, they're describing something far more fundamental than the distribution of galaxies or the curvature of spacetime around massive objects. They're describing the intrinsic geometry of the universe at its largest scales, a property that determines whether parallel lines remain, parallel, converge, or diverge as they extend through space. There are three basic possibilities, each with profound implications for the question of cosmic boundaries. The universe could be flat, which is what we call Euclidean geometry, the familiar geometry of everyday experience where the angles of a triangle add up to exactly 180 degrees and parallel lines never meet. In a perfectly flat universe that extends infinitely in all directions, there would be no edge, no boundary, just an endless expanse of space containing an infinite number of galaxies. Alternatively, the universe could have positive curvature, like the surface of a sphere. In such a universe, parallel lines would eventually converge. Triangles would have angles summing to more than 180 degrees. And most intriguingly, the universe would be finite in volume, while having no edge or boundary. Just as the surface of Earth is finite, yet has no edge, you can fall off. A spaceship traveling in a straight line in a spherically curved universe would eventually return to its starting point, having circumnavigated the entire cosmos. The third possibility is negative curvature, like a saddle shape, where space curves away from itself, parallel lines diverge, and the universe would be infinite in extent, with angles in triangles summing to less than 180 degrees current measurements, particularly from detailed observations of the cosmic microwave background, suggest that the universe is remarkably, almost suspiciously flat. The curvature, if any exists at all, must be so slight that the observable universe is many times larger than the distance over which that curvature would become apparent. This flatness presents its own mystery because inflation theory predicts this flatness. But the precision with which the universe appears flat suggests either that inflation worked exactly as the theory predicts, that the universe is vastly larger than the observable portion, or perhaps that our understanding is still incomplete. Imagine yourself as a two-dimensional being living on the surface of a balloon, a creature with no concept of up or down, no ability to perceive anything beyond the surface that constitutes your entire reality. As you travel across this surface in any direction, you never encounter an edge or boundary. You could journey forever in what seems like a straight line and eventually return to your starting point without ever feeling like you'd turned around. From your perspective, your universe would seem potentially infinite, an endless plane extending in all directions. Yet an observer in 3 dimensions, watching this balloon from outside, would see immediately that your universe is finite, bounded by the surface of the balloon, which has a measurable surface area. Moreover, if this balloon were being inflated, every point on its surface would be moving away from every other point. You and your fellow two-dimensional beings would observe that distant regions of your universe were receding at speeds proportional to their distance, faster the farther away they were. This is precisely what we observe in our three-dimensional universe. Galaxies are receding from us in all directions, and the farther away they are, the faster they're receding. The balloon analogy is powerful because it helps us understand how our universe might be finite yet unbounded. But it also points to a more profound possibility. Just as the two-dimensional surface of the balloon is curved through a third spatial dimension, our three-dimensional universe might be curved through a fourth spatial dimension, one that we cannot perceive or point to, but which exists nonetheless in the mathematical description of reality. In such a scenario, our universe could be the three-dimensional surface of a four-dimensional hypersphere, finite in extent, yet having no edge or boundary. The total volume would be finite, calculable, and yet no matter which direction we traveled, we would never encounter a wall or barrier. We would simply curve back around through this higher dimension, eventually returning to our starting point after traversing the entire circumference of the cosmic hypersphere. Mathematics offers us tools to think about infinity that go far beyond the simple notion of endlessness, and these tools become essential when grappling with cosmological infinities. The German mathematician Georg Cantor revolutionized our understanding of infinity in the late 19th century by demonstrating that not all infinities are created equal, that there are, in fact, different sizes of infinity, some vastly larger than others. Consider the counting numbers 1, 2, 3, and so forth, extending forever. This is an infinite set, and Cantor called this particular infinity countable, because you could, in principle, enumerate its members, assigning each one a position in the sequence. Now consider all the real numbers between 0 and 1, including all the fractions and irrational numbers like the square root of 2 or pi. This set is all infinite, but it's a different, larger infinity. Cantor proved that you cannot create a list that includes all these real numbers. No matter how you try to enumerate them, you'll always miss infinitely many. This larger infinity is uncountable, and it's infinitely larger than the infinity of counting numbers. When we apply these concepts to cosmology, fascinating possibilities emerge. The universe might be infinite in spatial extent, containing an infinite number of stars and galaxies, yet finite in other properties. For instance, if the laws of physics only permit a finite number of distinct quantum states within any given volume of space, then an infinite universe would necessarily repeat patterns. There would be regions, infinitely far away, where matter happened to arrange itself in exactly the same configuration as here, creating perfect copies of Earth, of you, of every moment of your life. This isn't science fiction. It's a logical consequence of infinite space combined with finite physical possibilities. Alternatively, the universe might be infinite in some dimensions or properties while being finite in others. It might be spatially infinite, but have existed for only a finite time. It might have infinite volume, but finite mass energy. The mathematical framework of infinity gives us the language to describe these nuanced possibilities, to distinguish between different types of endlessness and different ways that something can be both infinite and bounded. The cosmic microwave background radiation, often called the afterglow of the Big Bang, provides our most ancient snapshot of the universe, an image of the cosmos when it was merely 380,000 years old, a mere infant compared to its current age. This radiation detected as a faint glow of microwave energy coming from all directions in space, has been cooled by the expansion of the universe from the searing temperatures of the early cosmos to a frigid 2.7 degrees above absolute zero. But it's not perfectly uniform. When we map this radiation with exquisite precision, using satellites like COBE, WMAP, and most recently Planck, we see tiny temperature fluctuations, variations of only about 1 part in 100,000. But these minute differences carry enormous information. They represent the seeds of all cosmic structure, the quantum fluctuations that would eventually grow under gravity's influence to become galaxies, clusters, and the vast cosmic web we observe today. The statistical properties of these fluctuations, their size distribution, their angular correlations, tell us about the geometry and composition of the universe with stunning precision. One of the most important measurements we can extract from the cosmic microwave background is the universe's curvature. If the universe were positively curved like a sphere, light traveling from opposite sides of the early universe to reach us would have traversed a shorter path than in a flat universe, and the apparent size of fluctuations in the cosmic microwave background would appear larger. If the universe were negatively curved like a saddle, the opposite would be true. The remarkable result from decades of increasingly precise measurements is that the universe appears to be flat to within less than 1% margin of error. This flatness, combined with other measurements, tells us that if the universe curves back on itself, it must do so on scales vastly larger than the observable universe. Another crucial insight from the cosmic microwave background concerns topology. If the universe were finite and wrapped back on itself, we might be able to detect this by finding matched circles in the cosmic microwave background, pairs of circles with identical patterns that represent the same physical region of space seen in two different directions. Astronomers have searched for such matched circles and found none, which either means the universe is infinite or finite, but larger than we can observe, or wrapped in a topology complex enough that the matched patterns don't produce obvious circles. Topology, the mathematical study of shape and connectivity, offers some of the most exotic possibilities for how the universe might be structured. Unlike geometry, which concerns distances and angles, topology focuses on which points connect to which, how space is stitched together, the fundamental way that different regions relate to one another. A universe could be flat in its local geometry, yet have global topological properties that make it finite. Consider a classic video game like Asteroids, where a spaceship leaving the right edge of the screen reappears on the left edge, and leaving the top brings you back at the bottom. The screen appears flat, and locally the geometry is Euclidean, but globally the space has the topology of a torus, a donut shape. If our three-dimensional universe had analogous properties, you could travel in one direction and eventually arrive back where you started. Not because space is curved into a sphere, but because space is stitched together in a way that connects distant regions. This is called a three-torus, and it would make the universe finite in volume while preserving the flat geometry that observations suggest. Even more exotic topologies are possible. The universe could have the topology of a dodecahedral space, where opposite faces of a dodecahedron are connected, but with a specific twist. In such a universe, looking in different directions through space would allow you to see the same galaxies and galaxy clusters repeated in different parts of the sky, like looking at multiple reflections in a hall of mirrors. Except these wouldn't be reflections, but actual different paths that light could take through the multiply connected space. Some cosmologists have claimed to find hints of such topological structure in the cosmic microwave background, though these claims remain controversial and unconfirmed. The appeal of these topological models is that they resolve certain conceptual issues. A finite universe raises the question of what lies beyond its edge, but a finite universe with non-trivial. Topology has no edge, no boundary, no outside to worry about, yet it contains only a finite volume of space. It's a way of having your cosmological cake and eating it too, achieving finiteness without boundaries. The concept of horizons in cosmology extends far beyond the simple notion of how far we can see, encompassing subtle and profound limits on cosmic knowledge and interaction. The particle horizon represents the boundary of the observable universe, the distance beyond which light has not had time to reach us since the Big Bang. Everything inside this horizon is potentially observable. Everything beyond it is forever hidden from our past and present observations. But there's another horizon, perhaps more philosophically troubling, called the event horizon of the universe, sometimes termed the cosmic event horizon. This represents the ultimate limit of the regions of space we could ever reach or communicate with. Even if we started traveling right now at speeds approaching that of light and continued forever. The accelerating expansion of the universe, driven by the mysterious dark energy that permeates space, creates this event horizon. Galaxies beyond this boundary are receding from us so rapidly that even light leaving Earth right now will never catch up to them. The space between us and them is expanding faster than light can traverse it. This means there are galaxies we can currently see, whose ancient light has reached us from the distant past, but which we could never visit, never communicate with, never influence in any way, regardless of how long we waited or how fast we traveled. These galaxies are observable, but not reachable, visible, but forever beyond interaction. The existence of this cosmic event horizon means that the universe, even if infinite in spatial extent, divides into causally disconnected regions. Our observable patch of the universe will eventually become isolated, an island of stars and galaxies that can interact with each other, but which remain forever separated from the rest of cosmic reality. In a very real sense, the cosmic event horizon represents an edge to our universe. Not an edge to space itself, but an edge to the region of space that can ever be part of our cosmic story. It's a boundary drawn not by walls or barriers, but by the expansion of space itself. A boundary that's constantly shifting, swallowing up more galaxies as they cross from the reachable into the unreachable, from the causally connected to the causally disconnected. The multiverse hypothesis, arising naturally from the theory of eternal inflation, offers perhaps the most dramatic resolution to the question of cosmic boundaries. If inflation occurred in our region of space, transforming a tiny quantum fluctuation into a vast cosmos, there's no reason to think it happened only once or only here. The quantum fields that drove inflation would have fluctuated throughout space, creating bubbles of inflation scattered through a larger background space. Each bubble, expanding exponentially, would become its own universe, with potentially different physical properties, different constants of nature, different particles and forces. Our observable universe would be just one such bubble, one pocket universe in an eternally inflating sea of space that produces bubble universes without end. In this scenario, our universe absolutely has an edge. It's the boundary between our bubble and the inflating space beyond, or between our bubble and other bubbles that might have collided with ours. But the multiverse as a whole would be infinite, spatially eternal, forever producing new bubble universes as quantum fluctuations trigger new episodes of inflation. This gives us both infinity and an edge simultaneously, but in a nested way. Our universe has edges, but it exists within an infinite superstructure. The physics at the boundary of our bubble universe would be exotic beyond imagination. The inflation field would have different values on either side of the boundary, meaning the vacuum state of space itself would be different. The very laws of physics might differ across this boundary. If we could somehow approach it, we'd see a wall where the fundamental nature of reality changed, where particles and forces transformed into something unrecognizable. Of course, this boundary is probably forever beyond our reach, receding from us faster than light as our bubble continues to expand internally, while being embedded in the still inflating space beyond eternal inflation, also resolves certain fine-tuning problems in cosmology. Our universe appears exquisitely calibrated for the existence of complex structures like stars, planets, and life. The fundamental constants of nature, the strength of forces, the masses of particles, all seem to fall within a narrow range that permits such structures to form. In a single universe, this fine-tuning seems almost miraculous, demanding explanation. But in an infinite multiverse producing infinite variations, every possible combination of physical constants would be realized somewhere. We find ourselves in a universe with life-permitting properties, not because the universe was designed for life, but because only in such universes would beings like us exist to ask the question. The multiverse makes our universe's properties less mysterious by embedding us in a vastly larger context. The philosophical implications of cosmic boundaries cut to the heart of some of humanity's oldest questions about existence and reality. If the universe has an edge, a genuine boundary beyond which space itself does not exist, what could possibly lie on the other side? The question seems to demand an answer, yet any answer appears logically problematic. If there's something beyond the boundary, then that something is also part of physical reality, and the boundary wasn't really the edge of the universe after all. If there's absolutely nothing beyond the boundary, not even empty space, what does that even mean? Nothing is usually conceived as empty space, the absence of matter and energy, but still a place where things could exist. But at the edge of the universe, we're talking about the absence of space itself. Not just empty space, but no space at all. This is a concept that breaks our intuitions because every experience we've ever had involves being somewhere, existing in space. The notion of no space existing, no there for anything to be, no distance to measure or direction to point, seems incoherent. Philosophers and physicists have wrestled with these questions for centuries, often concluding that the question of what lies beyond is simply a category error, a question that appears meaningful but actually isn't. Asking what exists outside the universe, they argue, is like asking what's north of the North Pole. The question uses meaningful words in a grammatically correct structure, but doesn't actually refer to anything coherent. The North Pole is defined as the northernmost point. There is no direction that is north from there. Similarly, the universe is defined as everything that exists. There is no outside to it by definition. Yet this logical resolution often feels unsatisfying, like we're dodging the question rather than answering it. The human mind demands to know about boundaries and edges, to understand limits and extents, and telling someone that their question doesn't make sense rarely quiets that demand. Some physicists have proposed that the boundary of the universe, if it exists, might be where the laws of physics themselves break down, where the mathematical structure that governs reality becomes undefined. This would make the edge not a place but a limit to the applicability of physical law, a boundary beyond which concepts like space, time, causality cease to have meaning. Dark energy, the mysterious force driving the accelerated expansion of the universe, plays a crucial role in creating cosmic boundaries even in an infinite universe. discovered in the late 1990s through observations of distant supernova, dark energy appears to be a property of space itself, an inherent tendency for space to expand even in the absence of any matter. Radiation. The more space there is, the more dark energy exists, and the more space expands, creating a runaway effect that causes the expansion rate to accelerate over time. In the early universe, when everything was compressed into a smaller volume, the density of matter and radiation was high enough that gravity dominated over dark energy, slowing the expansion. But as the universe expanded and matter became more dilute, dark energy eventually gained the upper hand, and about 6 billion years ago, the expansion began to accelerate. This acceleration has profound implications for the long-term structure of the universe. As the expansion accelerates, distant galaxies recede from us ever faster. The cosmic event horizon, the boundary beyond which we cannot reach or communicate, is created by this acceleration. Galaxies that are currently just beyond this horizon are forever lost to us, their light racing toward us, but never bridging the gap, as space expands faster than light can traverse it. Over cosmic timescales, this horizon will envelop more and more galaxies. Structures that are currently gravitationally bound, like galaxy clusters, will remain together, but everything beyond our local group of galaxies will eventually accelerate beyond the cosmic event horizon. In trillions of years, future observers in our galaxy would see a very different universe. A small collection of local galaxies in an increasingly empty void, as everything beyond is carried away beyond the observable universe. The expansion will continue to accelerate, and the horizon will continue to shrink in terms of what new regions it can encompass, eventually becoming smaller than the particle horizon, meaning that the universe we can observe will be larger than the universe we can theoretically reach. Dark energy thus creates a dynamic boundary, one that changes over time, swallowing up more and more of the cosmos and reducing the portion of the infinite universe that can ever be part of our causal future. In this sense, even an infinite universe has an effective edge for any particular observer, a boundary beyond which the rest of reality becomes permanently inaccessible. The search for unusual topology in the universe represents one of the most ambitious observational programs in cosmology, an attempt to detect whether space wraps back on itself in ways that would make the universe finite, despite appearing flat. Several approaches have been developed to search for these topological signatures. One method looks for matched circles in the cosmic microwave background. If the universe has a finite topology, light from the early universe could have taken multiple paths to reach us, traveling in different directions through the multiply connected space. Where these paths intersect our past light cone, they would create circles on the cosmic microwave background sky that show identical patterns of temperature fluctuations. Finding such matched circles would be smoking gun evidence for finite topology. Extensive searches using data from the WMAP and Planck satellites have been conducted, looking for pairs of circles with correlated temperature patterns, but no convincing detections have been made. This either means the universe is infinite, or its finite size is larger than the observable universe, so that the topological features lie beyond our horizon, or the topology is more complex than simple models predict, creating signatures too subtle to detect with current data. Another approach examines the distribution of galaxies themselves. In a universe with finite topology, we might see the same galaxy or galaxy cluster appearing in different parts of the sky, like seeing multiple images of the same candle in a hall of mirrors. The challenge is distinguishing genuine repeated structures from the statistical likelihood that similar structures would form independently in different regions of space. Surveys mapping the three-dimensional positions of millions of galaxies have searched for such repeating patterns in the cosmic web, again without clear detections, pushing any topological scale to beyond the observable. Universe. A third method involves studying the pattern of correlations in the cosmic microwave background at the very largest scales. If the universe has a finite topology smaller than the observable universe, this would suppress correlations at scales larger than the finite size, creating a characteristic signature in the power spectrum of temperature fluctuations. Some researchers have claimed to see hints of such suppression at the largest observable scales. But these claims remain controversial, with others arguing that the apparent suppression could be a statistical fluke, or could result from systematic errors in data analysis. The observational constraints are increasingly stringent. If the universe has a finite topology, it must be at least as large as, and probably significantly larger than, the observable universe, making it effectively indistinguishable from an infinite universe in terms of our observations. The concept of heat death offers a temporal perspective on cosmic boundaries, suggesting that even an infinite universe might have an endpoint in time. The second law of thermodynamics states that the total entropy, or disorder, of any closed system must always increase or remain constant, never decrease. The universe as a whole is the ultimate closed system, containing everything that exists, and so this law applies to the cosmos itself. Every irreversible process, from the burning of stars to the formation of black holes to the heat dissipating from your body right now, increases the universe's total entropy. In the very distant future, assuming dark energy continues to drive accelerated expansion, the universe will become increasingly cold, dark, and empty. Stars will exhaust their nuclear fuel and die, some exploding as supernovae, others fading as white dwarfs, or becoming black holes. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that allows black holes to slowly leak energy over immense timescales that dwarf the current age of the universe, as much as that age dwarfs a human lifetime. After approximately 10 to the 100 years, even the largest black holes will have evaporated completely, leaving behind nothing but a thin soup of photons, neutrinos, and perhaps electrons and positrons, all redshifted to infinitesimal energies by cosmic expansion. The universe will approach a state of maximum entropy, where no useful energy remains, where no structure persists, where nothing can happen anymore, because all possible energy conversions have already occurred. This is heat death, and while the universe will continue to exist in this state indefinitely, it will be a static, unchanging existence. Time will still pass, but nothing will mark that passage. No events will occur, no information will be processed or transmitted, no structure will form or evolve. This represents a kind of edge to the universe, not in space, but in meaningful time, a boundary beyond which the universe's story effectively ends even though the universe itself persists. Interestingly, this fate appears independent of whether the universe is spatially infinite or finite. An infinite universe would approach heat death just as certainly as a finite one, with entropy increasing without bound, even as it spreads across infinite space. The edge represented by heat death is thus a temporal boundary, an end to cosmic history if not to cosmic existence, a final state from which no further evolution is possible. Quantum mechanics introduces additional complications and perspectives on the nature of space and the possibility of infinity. At the smallest scales, approaching what's called the Planck length, approximately 10 to the negative 35 meters, quantum fluctuations of spacetime itself become significant. At these scales, space and time stop behaving like the smooth, continuous fabric described by classical general relativity and become something altogether different, a seething quantum foam where the very notions of distance and duration become fuzzy and ill-defined. Some approaches to quantum gravity, such as loop quantum gravity, suggest that space itself might be quantized, made up of discrete units or quanta, rather than being infinitely divisible. If this is correct, then space would be more like a digital image, composed of pixels of some minimum size, rather than an analog continuum that can be divided forever. This discreteness would have profound implications for the concept of spatial infinity. A truly infinite universe would contain an infinite number of these spatial quanta. But the very notion of assembling an infinite number of discrete units into a coherent whole raises mathematical and physical questions. Can a discrete structure ever really embody infinity in the same way that a continuous space can? Other quantum considerations arise from the holographic principle, derived from studying black holes and their information content. This principle suggests that the maximum information that can be contained in any region of space is proportional to the surface area of that region, measured in Planck units, rather than to its volume. This implies a fundamental connection between information, space, and boundaries. The holographic principle has led some physicists to propose that our three-dimensional universe might actually be a kind of hologram, a projection from information encoded on a two-dimensional boundary at the edge of space. In this view, the boundary is fundamental and the volume is derived, reversing our usual intuitions about dimensionality. While these quantum considerations don't definitively answer whether the universe is infinite or bounded, they suggest that at the most fundamental level, space might be very different from what we imagine, potentially making the question of infinity versus boundaries dependent on which description of reality we adopt, quantum or classical, discrete or continuous. The simulation hypothesis, while speculative, and often relegated to philosophy rather than physics, provides yet another framework for thinking about cosmic boundaries and infinity. If our universe is actually a computational simulation, as some philosophers and physicists have seriously suggested might be possible and even likely, then questions of infinity and edges take on entirely new meanings. A simulated universe could be infinite within its own rules, with the simulation calculating spacetime and physical laws in any region that observers within the simulation are able to access or measure. From inside such a simulation, the universe would appear to follow consistent laws, to extend in all directions, to potentially be infinite in extent. Yet the simulation itself would be fundamentally finite, existing as software running on some substrate in a higher reality. The simulation would have boundaries defined by its computational limits, by what regions of simulated space the simulator chooses to render, in detail versus leaving undefined until needed, much like a video game that only fully renders the environment near the player's current location. This creates a nested understanding of infinity and boundaries, infinite from within, finite from without. The simulator might implement rules that make the simulated universe appear infinite to its inhabitants, while actually using finite computational resources through clever algorithms. For instance, the simulation might use procedural generation, computing the properties of distant galaxies only when simulated observers point their telescopes in that direction, storing just enough information to ensure consistency when those regions are observed again. The edge of such a universe would be defined by the limits of what the simulation computes, and beyond that edge, space wouldn't merely be empty or inaccessible. It would literally not exist even as a potential until the simulation decided to create it. We would have no way of detecting. We were in such a simulation if it were implemented competently enough, as any test we could perform would be constrained by the simulation's rules. The simulation hypothesis thus provides a logically consistent framework where infinity and boundaries coexist through a hierarchy of reality levels, though it pushes the ultimate question of infinity versus boundaries up one level to the simulator's universe. Current and future observational capabilities may help resolve some aspects of the infinity versus boundary question, even if the full answer remains forever beyond certain knowledge. The James Webb Space Telescope, launched in 2021, can observe the universe at unprecedented distances and redshifts, looking back to when the first galaxies were forming just a few 100 million years after the Big Bang. By studying these ancient galaxies and the intergalactic medium in which they're embedded, astronomers can better constrain models of cosmic inflation and the large-scale structure of space ground-based observatories like the Vera Rubin Observatory, with its capability to survey the entire visible sky every few nights. We'll map the distribution of galaxies with unprecedented completeness, potentially revealing subtle patterns that might indicate topological features or unusual geometry. The next generation of cosmic microwave background experiments, whether space-based or ground-based at sites like the South Pole, aim to measure the polarization of this ancient light with exquisite precision, potentially detecting the signature of gravitational waves from inflation or revealing subtle geometrical features. Gravitational wave observatories, from the current LIGO and Virgo detectors to planned space-based observatories like LISA and proposed next-generation ground-based facilities, will probe the universe using an entirely different messenger. Ripples in spacetime itself produced by colliding black holes, merging neutron stars, or potentially from the inflationary epoch. These gravitational waves carry information about the geometry and topology of space through which they've traveled. If the universe has unusual topology, gravitational waves might take multiple paths to reach us, arriving at different times or with correlated patterns that would reveal that multiply-connected structure. Pulsar timing arrays, networks of precisely measured millisecond pulsars, are already detecting evidence of gravitational waves at very long wavelengths. Waves that might have originated from the early universe or from supermassive black hole mergers. And these observations will improve dramatically with larger arrays and longer observation baselines. Yet even with all these tools, there may be fundamental limits to what we can learn. If the universe's curvature or topological scale is larger than the observable universe, we may never detect it directly, able only to place ever-improving lower bounds on how large it must be. The measurement problem in cosmology represents a profound challenge to definitively answering questions about the universe's extent and boundaries. Unlike laboratory experiments, where we can repeat measurements under controlled conditions, test different samples, and isolate variables, we have access to only one universe observed from only one location. This is sometimes called the problem of cosmic variance. We cannot know whether what we observe in our cosmic neighborhood is typical or unusual, representative or anomalous. If the universe is infinite or even just vastly larger than the observable portion, different regions might have different properties. The density of matter might vary on scales larger than we can see, or the strength of physical constants might fluctuate across cosmic distances, or the topological structure might be different in regions forever beyond our horizon. We would have no way to know because we can only sample the one region we inhabit. This makes certain cosmological questions fundamentally difficult or impossible to answer with complete certainty. We can observe that our region of the universe is very flat, but we cannot know whether this flatness persists beyond the cosmic horizon or whether. Space curves dramatically in regions we cannot observe. We can measure that dark energy appears constant in density throughout our observable volume, but we cannot verify whether this constancy continues throughout an infinite universe, or whether dark energy varies in the multiverse beyond. Even if our theoretical models predict certain features like infinite extent or topological structure, we are constrained to testing those predictions only within our cosmological sample size of one observable universe. Statistical cosmology attempts to work around these limitations by using probability arguments and anthropic reasoning, asking what we should expect to observe given different theoretical scenarios and accounting for selection effects. For instance, if the universe is infinite, we should find ourselves in a typical region rather than an unusual one, because typical regions vastly outnumber unusual ones. This kind of reasoning can help constrain theories, but it requires assumptions about probability measures over infinite sets, which themselves remain controversial and potentially underdetermined by any possible observation. The multiverse hypothesis exacerbates this problem, because if there are infinitely many bubble universes with different properties, our observations tell us about our bubble, but potentially nothing about the ensemble as a whole. We might be in a very atypical bubble, one whose properties are extraordinarily unusual, but which must exist somewhere in an infinite multiverse, simply because all possibilities are realized. This makes predictions difficult and testing nearly impossible, pushing some of these questions beyond the traditional realm of empirical science into territory that might be forever speculative. As we synthesize the various perspectives we've explored, a coherent picture begins to emerge, though it's a picture that challenges our intuitions at every turn. The universe appears to be both infinite and bounded, but in different senses, along different dimensions, from different perspectives. The observable universe has a definite edge, created not by any wall or barrier, but by the finite speed of light and the finite age of the cosmos. This is an informational boundary, a limit to what we can know about the universe's extent, rather than a limit to space itself. Beyond this horizon, the universe almost certainly continues, possibly forever. If cosmic inflation occurred as our best theories suggest, the universe is vastly larger than what we can observe, potentially infinite in spatial extent, containing an endless number of galaxies and stars extending in all directions without limit. Yet even in this infinite expanse, there are boundaries of a different sort. The cosmic event horizon, created by the accelerating expansion driven by dark energy, represents a boundary to the region we can ever interact with or reach, even given infinite time. This creates causally disconnected patches within an infinite universe, islands of space that can communicate internally but remain forever isolated from each other. The geometry of space adds another layer to this picture. Current observations suggest the universe is flat or nearly so, which in an unbounded geometry would imply infinite extent. But geometry and topology are separate considerations, and the universe could be flat, yet finite, if space wraps back on itself in ways we haven't detected. This would make the universe finite in volume, yet boundless in the sense that you could travel forever without encountering an edge, eventually returning to your starting point. The absence of detected topological signatures suggests that if such structure exists, it must operate on scales larger than the observable universe, making the distinction between finite and infinite effectively meaningless for practical purposes. We can observe and interact only with the portion of space within our cosmic horizon. and whether space continues infinitely beyond or closes. Back on itself at larger scales makes no operational difference to our measurements or experiences. The multiverse framework offers perhaps the most elegant resolution to the paradox in the documentary's title. Within the eternal inflation scenario, our universe, the region that emerged from our particular inflationary event, has an edge where our bubble meets the still inflating space beyond, or where it might abut other bubble universes. This edge is as real and definite as any boundary could be, representing a place where the fundamental properties of space itself change discontinuously. But this bounded universe exists within an infinite multiverse, a space that continues to inflate eternally, producing bubble universes without end. The infinity is real, encompassing an endless ensemble of universes with varying properties. But each individual universe within that ensemble has boundaries, edges where its domain ends and something else begins. This hierarchy resolves the apparent contradiction. Infinity and edges coexist, but at different levels of cosmic structure. Quantum mechanics adds yet another dimension to our understanding, suggesting that at the smallest scales, space itself might be discrete rather than continuous, made of indivisible quanta that cannot be subdivided further. If this is the case, then true mathematical infinity might not be realized in physical space, which would instead consist of a very large but finite number of spatial units, even if that number is so vast that it might as well be infinite for any practical purpose. The Planck length provides a natural unit for such quantization, and an observable universe with a radius of 46.5 billion light-years contains approximately 10 to the power of 185 Planck volumes. If the entire universe is 1,000 times larger than the observable portion, that would increase this number, but it would remain finite, a countable number of discrete spatial units. Yet this discrete structure would be utterly invisible at the scales we can measure, and the universe would appear continuous and potentially infinite from our perspective. The temporal dimension provides another sense in which the universe might have boundaries even while being infinite in space. The universe had a beginning in time, the Big Bang event some 13.8 billion years ago, when space, time, matter, and energy all came into existence together. Before this moment, if before even makes sense in this context, there was no universe, no space, no time. The Big Bang represents a temporal edge, a boundary to the past beyond which our physical theories break down and our questions may lose meaning. Looking toward the future, the heat-death scenario suggests another kind of temporal boundary, not an end to the existence of the universe, but an end to its capacity for change, novelty, and complexity. The journey from Big Bang to heat-death, from infinite density and temperature to infinite dilution and cold, represents the universe's arrow of time, a directionality imposed by increasing entropy. Within this temporal span, the universe evolves, stars form and die. Galaxies merge and separate, and complexity emerges and eventually dissipates. The universe might be infinite in spatial extent, but its meaningful history, the period during which interesting things can happen, is bounded between these two temporal horizons. Philosophically, the question of cosmic boundaries forces us to confront the limits of human understanding and the potential gap between what exists and what we can know. If the universe extends infinitely beyond our cosmic horizon, there are facts about reality that we can never verify, regions of space whose properties we can never measure, events that have no causal connection to anything in our observable patch. This creates an interesting epistemological situation where we might have good theoretical reasons to believe in the existence of this vast unobservable reality based on laws of physics tested in the region we can observe. Yet we must acknowledge that this belief rests on an extrapolation that can never be directly verified. The universe beyond our horizon is real, in the ontological sense, if it exists at all, but it's forever beyond the reach of empirical science. We must rely on theoretical elegance, mathematical consistency, and the principle that the laws of physics we observe locally continue to apply universally, even in regions we can never access. The question of what lies beyond the edge, if the universe has an edge, ultimately may be a question without an answer, not because we lack sufficient data or powerful enough theories, but because the question itself may not correspond to any coherent concept. The universe, by definition, is everything that exists. To ask what lies beyond is to ask about a region that simultaneously is part of reality, and therefore part of the universe, and is not part of the universe. This logical contradiction suggests that the question contains a category error. Yet this abstract philosophical resolution doesn't satisfy our intuitive need for understanding, our desire to grasp the complete picture. Perhaps this is a limitation we must accept, a recognition that our cognitive machinery, evolved to navigate a middle-scale world of objects and territories, may not be equipped to fully grasp the nature of cosmic totality. Modern cosmology has revealed that the universe operates according to principles that consistently violate our intuitions. Space itself can expand faster than light. Time can dilate based on velocity and gravitational fields. Particles can exist in superposition, occupying multiple states simultaneously until measured. The universe's average density appears to be dominated by forms of matter and energy that we cannot see and have never directly detected in terrestrial laboratories. Against this backdrop of counterintuitive reality, the notion that the universe might be both infinite and bounded shouldn't be surprising. It's simply another way in which the cosmos refuses to conform to the categories and dichotomies that seem natural to human thought. The various edges and infinities we've discussed, the particle horizon and event horizon, the potential topological boundaries and multiverse bubble walls, the temporal boundaries of Big Bang and heat death, the quantum graininess at Planck scales. These aren't competing alternatives, but complementary aspects of a complex reality. The universe exhibits boundary-like features in multiple ways, while potentially being infinite in extent. Both aspects are real. Both are important for understanding cosmic structure and evolution, and both must be incorporated into our comprehensive picture of reality. The apparent paradox arises from our initial assumption that infinity and boundaries are mutually exclusive, an assumption that works well in everyday contexts but breaks down when applied to the cosmos as a whole. Future generations will have access to better data, more sophisticated theories, and perhaps conceptual frameworks we cannot currently imagine. They may resolve questions that seem intractable to us, or they may discover new layers of complexity that make our current puzzlement seem naive. The history of cosmology suggests that answers often raise new questions, that each mystery solved reveals deeper mysteries. The question of cosmic infinity and boundaries may never be fully resolved, not because the universe is inherently mysterious in some mystical sense, but because complete knowledge may require observations and measurements that are physically impossible, blocked by the very structure of space-time itself. What we can say with confidence is that the universe is far larger than the portion we can observe. If space extends infinitely beyond our cosmic horizon, then everything we've ever observed, every star and galaxy and cosmic structure, represents an infinitesimally small fraction of reality, a tiny bubble of knowledge in an endless sea of existence. If the universe is finite but very large, the conclusion is similar. We occupy a small, perhaps typical, perhaps unusual region of a vast cosmos, most of which we cannot access. Either way, humility is warranted. Our species has existed for a few 100,000 years. We've understood that the universe extends beyond Earth for only a few centuries, and we've known about cosmic expansion for less than a century. We are early in the process of understanding cosmic structure, and much remains unknown. The practical implications of these cosmic boundaries are minimal for everyday life, or even for most of astronomy, but the philosophical and existential implications are profound. We live in a universe that may be infinite in extent, yet bounded by horizons we cannot cross. Infinite in duration, yet bookended by temporal boundaries. Infinite in its quantum possibilities, yet seemingly governed by consistent laws. This universe is both our home and an eternal mystery, both comprehensible through science and ultimately beyond complete knowledge. The regions of space we can observe represent our cosmic neighborhood, but vast realms exist beyond, forever hidden by the speed of light and the expansion of space. Standing under a dark sky, gazing at the stars scattered across the celestial sphere, we're seeing ancient light from galaxies millions and billions of light years distant. Each photon has journeyed across cosmic voids, maintaining its straight path through expanding space to end its journey in our eyes or telescopes. These photons come from the observable universe, from within our cosmic horizon, from the region we can potentially learn about. But beyond, in the darkness between the galaxies, we can see space continues. More galaxies exist there, more stars, more worlds, all following the same physical laws, all part of the same cosmic story, but forever beyond our ability to observe or influence. The edge is not a wall, but a horizon, receding as we approach, always maintaining the same distance ahead of us as we race forward through time at its inexorable pace. The universe may be infinite, extending forever in all directions, containing infinite stars and infinite worlds, realizing every possible configuration of matter an infinite number of times. Or it may be finite but unbounded, wrapping back on itself through dimensions we cannot perceive, vast but ultimately limited in extent. Or it may be one finite bubble in an infinite multiverse, possessing clear boundaries where it meets other realities. Current observations cannot definitively distinguish between these scenarios, and future observations may face fundamental limits on resolving the question. We are left with provisional answers based on our best current theories and observations. Answers that combine aspects of infinity and boundaries in ways that challenge our intuitive categories. What remains certain is that the universe is magnificent in scale and complexity, operating according to physical principles we can investigate and understand, at least partially. The question of whether the universe is infinite and has an edge leads us through some of the most profound territory in physics and cosmology, challenging us to expand our conceptual frameworks, to think more carefully about space, time, causality, and existence itself. The answer, whatever it might be, changes nothing about our daily lives, yet it speaks to something deep in the human spirit, our desire to understand the nature of reality, to know our place in the cosmos, to grasp the ultimate structure of existence. Perhaps the most honest answer we can give is that the universe is both infinite and bounded, depending on what we mean by those terms, which aspects of cosmic structure we're considering. and from what perspective we ask the question. The observable universe has clear edges defined by light and causality. The entire universe may be infinite in extent, yet bounded by the history of cosmic expansion. Our particular pocket of the multiverse may have edges where it meets other regions, while the multiverse itself continues without limit. The universe may be spatially infinite, but temporally bounded, existing for a finite time between its beginning and its eventual heat death. Space may be infinite in classical descriptions, but finite when quantum effects at Planck scales are considered. This multiplicity of answers isn't a failure of cosmology, but a reflection of the subtle and complex nature of reality itself. The universe doesn't conform to simple categories or intuitive dichotomies. It operates according to mathematical laws that permit structures and properties that seem paradoxical when translated into everyday language. Our task as observers and thinkers is not to force the universe into conceptual boxes that feel comfortable, but to adjust our understanding to match what observations and theories reveal, even when that requires embracing apparent contradictions or accepting limitations on knowledge. Whether the universe is infinite or bounded may be less important than the journey we take in trying to answer the question. This journey has led to remarkable discoveries about cosmic expansion, the Big Bang, inflation, the nature of space and time, the role of quantum mechanics in cosmology, and the possible existence of multiple universes beyond our own. It has pushed our observational capabilities to their limits and beyond, inspiring the construction of ever more powerful telescopes and detectors. It has forced us to develop new mathematical frameworks and theoretical tools, expanding the boundaries of human knowledge and capability. And it has provided a source of wonder and humility, reminding us that we inhabit a cosmos far grander and stranger than our ancestors ever imagined. A universe that may be infinite in extent, bounded by horizons, or somehow both simultaneously. A reality that defies simple description, but rewards careful investigation with profound insights into the nature of existence itself. The cosmos stretches out before us, vast and ancient, filled with billions of galaxies, each containing billions of stars, governed by elegant physical laws that we're still working to fully understand. Whether it extends infinitely in all directions or curves back on itself, at scales beyond our detection, whether it's one bubble in an infinite multiverse or the totality of existence, it remains our home, our origin, and the source of endless questions that drive us to explore, to observe, to theorize, and to wonder. The edge of the universe, if it exists, may lie forever beyond our reach, but the search for it expands the boundaries of human knowledge. And in that search, we discover not just facts about the cosmos, but truths about ourselves and our capacity to comprehend the incomprehensible, to grasp at infinity while standing on this small rocky world, orbiting an ordinary star in an unremarkable galaxy in what may be one of countless universes in an eternal cosmic sea. The implications of cosmic boundaries extend into unexpected territories when we consider the nature of information itself and its relationship to the structure of spacetime. Information, in the physical sense, is not an abstract concept, but something deeply embedded in the fabric of reality. Every particle, every quantum state, every configuration of matter and energy represents information about the universe's current state and history. The holographic principle, emerging from theoretical studies of black holes by physicists like Jacob Bekenstein and Stephen Hawking, suggests a profound connection between information, entropy, and the geometry of space. This principle proposes that all the information contained within a volume of space can be encoded on the boundary of that volume, on a surface measured in Planck units. It's as if a three-dimensional region is entirely described by a two-dimensional surface surrounding it. Much like a hologram, encodes three-dimensional images on a two-dimensional film. This counterintuitive idea has been strengthened by discoveries in string theory, particularly the ADS/CFT correspondence discovered by Juan Maldacena, which demonstrates a precise mathematical equivalence between a gravitational theory in a higher dimensional space and a quantum field theory without gravity on the boundary of that space. If the holographic principle applies to our universe, it suggests that the boundary, even if we cannot physically access it or observe it directly, plays a fundamental role in determining what happens within the volume. The edge becomes not merely a limit to space, but a substrate on which the reality of the interior is encoded. This leads to fascinating speculations about the nature of space-time emergence. Some theoretical physicists now believe that space itself is not fundamental, but rather emerges from more basic quantum information structures. In this view, the smooth, continuous space-time of our experience is a large-scale approximation. Much like the solid surface of a table emerges from quantum mechanical atoms that are mostly empty space. At the deepest level, reality might be a network of quantum entanglement, with space and distance arising from the pattern of how quantum information is correlated between different parts of the system. Brian Swingle, Mark van Raamsdonk, and others have shown how the geometry of space can emerge from the entanglement structure of quantum states, with regions that are strongly entangled corresponding to regions that are close together in space. In such a framework, the question of whether the universe is infinite or has boundaries becomes a question about the structure of this underlying quantum information network. An infinite universe would require an infinite network, an endless web of quantum correlations extending in all directions. A bounded universe might have a finite network, with the boundary representing a place where this network simply ends, where no further quantum systems exist to be entangled with the interior. Alternatively, the network might wrap back on itself, with boundary points connecting to other boundary points, creating a finite but unbounded topology in information space that manifests as a finite but unbounded physical space. The relationship between observers and cosmic boundaries raises profound questions about the nature of observation itself and the role of consciousness or measurement in defining reality. In quantum mechanics, the act of measurement plays a crucial role in determining the properties of a system, collapsing quantum superpositions into definite states. While this is well understood for laboratory-scale systems, its implications for cosmology remain deeply puzzling and controversial. If the universe exists in quantum superposition on scales larger, then what we can observe, does the unobserved portion have definite properties? Some interpretations of quantum mechanics, like the many-worlds interpretation, suggest that all possible quantum outcomes are realized in branching universes, which would multiply the question of cosmic boundaries across an infinite ensemble of parallel realities. Other interpretations, like objective collapse theories, propose that quantum states collapse into classical definiteness at certain scales or under certain conditions, even without observation, which might give the unobserved universe definite properties independent of our knowledge. The Copenhagen interpretation, traditionally the most conservative, struggles with cosmological questions because it requires an external observer, but there is no outside to the universe from which to observe it. These interpretive questions suggest that the boundary between the observable and unobservable universe might be more than just a limit on information transfer. It might represent a genuine divide between regions where the universe has definite classical properties and regions where it remains in quantum superposition, undefined until and unless causal connection with observers becomes possible. The mathematical structure of infinity itself deserves deeper examination in the context of cosmology. Georg Cantor's revolutionary work on infinite sets revealed that infinity comes in different sizes, a discovery that initially seemed like pure mathematics, but may have physical relevance. The smallest infinity, Aleph Null, is the cardinality of the counting numbers 1, 2, 3, and so on, forever. This is a countable infinity because you can, in principle, list its elements in a sequence. The next larger infinity, the cardinality of the continuum, is the number of points on a line, or the number of real numbers between 0 and 1. Cantor proved that no matter how you try to list real numbers, you'll always miss infinitely many, meaning this infinity is strictly larger than the infinity of counting numbers. Beyond this lie even larger infinities in an endless hierarchy, each transcending the one before. If the universe is spatially infinite in a continuous sense, it might contain a continuum of points, an uncountable infinity. But if space is discrete at the Planck scale, as quantum gravity theories suggest, then an infinite universe would contain a countable infinity of spatial units. This distinction might seem academic, but it has implications for questions like whether there are perfect copies of you elsewhere in the universe. In a universe with countable infinity and finite quantum possibilities, per region, perfect copies would necessarily exist infinitely far away in infinitely many locations. In a universe with uncountable infinity, the mathematical structure becomes richer and the question of duplicates becomes more subtle, depending on the measure theory used to assign probabilities to different configurations. The concept of cosmic inflation, while widely accepted as the best explanation for several observed features of the universe, itself raises questions about boundaries and infinity. During the inflationary epoch, quantum fluctuations in the inflation field were stretched to cosmic scales, becoming the seeds of all structure we observe today. But these quantum fluctuations were statistical in nature, meaning different regions of space underwent slightly different amounts of inflation, ending at slightly different times. In the eternal inflation scenario developed by Andre Linde, Alexander Vilenkin, and others, some regions of space never stop inflating. While our region transitioned out of inflation 13.8 billion years ago, settling into the slower expansion we observe today, other regions continued inflating. And within those regions, some patches transitioned out, while others continued. This process continues eternally into the future, with space always containing regions that are inflating and spawning new bubble universes. The mathematics of eternal inflation suggest that once inflation starts, it generically continues forever, in some regions, producing an infinite number of bubble universes with varying properties. Each bubble, including ours, has a boundary where the inflation field took on different values, where the phase transition from inflation to normal expansion occurred at a different time or in a different way. These boundaries are not static but dynamic, expanding as the bubble itself expands, but they represent genuine edges to individual universes within the eternal inflating multiverse. The physics at such boundaries would be exotic and unlike anything we experience in our everyday universe. The vacuum state of space itself would be different on either side of the boundary, with different vacuum energy densities giving rise to different effective cosmological constants. Particles and fields that are stable in our vacuum might be unstable in the neighboring vacuum, potentially decaying or transforming into different particles. The fundamental constants of nature, quantities like the strength of gravity, the mass of the electron, or the fine structure constant, that governs electromagnetic interactions might have different values across the boundary. These constants, which seem fundamental and unchangeable from our perspective, inside one bubble universe, might actually be environmental parameters that vary from bubble to bubble, determined by how the inflation field and other scalar fields settled into their ground states at the end of inflation in each region. This would mean that the laws of physics as we know them apply only within our bubble, and very different physics might govern other bubbles in the multiverse. The boundary between bubbles represents not just a spatial edge, but a transition zone where the very fabric of physical law transforms from one regime to another. Observationally detecting such a boundary, if one existed within or near our observable universe, would be extraordinary and unambiguous. We might see a region of sky where the cosmic microwave background temperature or polarization showed a sudden discontinuity, indicating that we were looking toward the edge of our bubble. We might observe galaxies near such a boundary being gravitationally affected by matter distributions on the other side, creating anomalous motions or tidal effects. Most dramatically, if another bubble had collided with ours in the past, the collision would have released enormous energy, creating a distinctive pattern of hot and cold spots in the cosmic microwave background, in a circular pattern centered on the collision point. Several research groups have searched for such collision signatures in cosmic microwave background data from Planck and other satellites, and while a few anomalous features have been identified, none have proven to be convincing evidence for bubble collisions. The absence of detected collisions tells us that if we live in a bubble universe, either we're far from its edges and far from any colliding neighbors, or bubbles are sufficiently far apart that collisions are rare, or our bubble is so large that the edges are well beyond our observable horizon. Each of these possibilities is consistent with eternal inflation theory, but would imply slightly different details about the inflationary process and the resulting multiverse structure. The Anthropic principle provides another lens through which to view cosmic boundaries and the question of infinity. The strong Anthropic principle notes that we should not be surprised to find ourselves in a universe with properties compatible with the existence of observers like us, because we could not exist in universes with properties that prevent the formation of stars, planets, or complex chemistry. If the multiverse is real and infinite, containing bubbles with every possible combination of physical constants and laws, then observers will necessarily find themselves in the subset of bubbles where conditions permit observer. Existence. This explains the otherwise mysterious fine-tuning of our universe's properties without requiring a designer or invoking extraordinarily improbable coincidences. Our universe appears fine-tuned for life, not because it was designed or because we're extraordinarily lucky, but because an infinite multiverse realizes all possibilities, and we necessarily observe from within one of the life-permitting examples. The Anthropic principle thus connects cosmic boundaries, the multiverse, and infinity to questions of existence and observation. The edge of our bubble universe, forever beyond reach though it may be, is essential to this anthropic explanation because it defines the region where one set of physical constants applies, distinguishing our observable universe from the infinite variety of other bubbles with different properties. Dark matter, the mysterious substance that appears to comprise about 85% of the universe's matter content, adds another dimension to our understanding of cosmic structure and boundaries. While dark matter doesn't emit, absorb, or reflect light, making it invisible to telescopes, we know it exists through its gravitational effects on visible matter, on the motion of galaxies within clusters, on the bending of light through gravitational lensing, and on the patterns in the cosmic microwave background. Dark matter appears to form an enormous cosmic web, with filaments stretching hundreds of millions of light years across. connecting galaxy clusters in a vast network that defines the large-scale structure of the universe. This cosmic web extends throughout the observable universe and presumably continues beyond our horizon into unobservable regions. If the universe is infinite, this web extends infinitely, an endless network of matter, both dark and luminous, with the same statistical properties repeating at all scales and in all directions. The existence of this large-scale structure provides another way of thinking about cosmic boundaries. While there may be no edge to space itself, there are edges to individual structures within space. Galaxies have edges where their density drops to match the intergalactic medium. Galaxy clusters have edges where the cluster's gravitational influence gives way to the expansion of space. Cosmic web filaments have edges where they transition to the voids between them. These are not boundaries to the universe, but boundaries within it. Organizational structures that divide the infinite whole into regions with different properties and densities. The question of whether the universe had a beginning is intimately connected to whether it has spatial boundaries. The Big Bang represents a temporal boundary, a moment 13.8 billion years ago, when the universe was in a state of infinite or near infinite density and temperature, from which it has been expanding and cooling ever since. But did the Big Bang represent the absolute beginning of time, the creation of space itself, or was it merely a transition from some earlier state? Some models of quantum cosmology, such as the Hartley-Hawking no-boundary proposal, suggest that time becomes space-like at extreme energies near the Big Bang, eliminating the singularity and removing the need for a temporal beginning. In this picture, asking what happened before the Big Bang is like asking what's north of the North Pole, a question that seems meaningful but actually isn't, because the framework that gives meaning to before breaks down. Other models propose a cyclic universe that undergoes infinite cycles of expansion and contraction, with each Big Bang being followed billions of years later by a big crunch that transitions into the next Big Bang. In such scenarios, the universe is temporally infinite despite having the Big Bang as a boundary to our current expansion phase. Still, other models invoke quantum cosmology or string theory to suggest the universe emerged from a quantum fluctuation in a pre-existing space, a kind of quantum tunneling event that created our cosmos from nothing or from a vacuum state. Each of these models has different implications for spatial infinity and boundaries, connecting the temporal structure of the universe to its spatial extent in ways that our classical intuitions about time and space fail to capture. The accelerating expansion of the universe, driven by dark energy, creates a dynamical situation where cosmic boundaries change over time. In the distant past, shortly after the Big Bang, the observable universe was much smaller because less time had elapsed for light to travel. The cosmic event horizon, beyond which we can never send or receive signals, was also different. As time goes forward, the particle horizon, the boundary of the observable universe, grows larger as light from more distant regions has time to reach us. But the cosmic event horizon, defined by the accelerating expansion, actually shrinks in comoving coordinates, encompassing fewer galaxies that we could potentially reach. This creates an interesting trajectory for our cosmic knowledge. For the next several billion years, we'll continue to see light arriving from increasingly distant regions of the early universe, gradually expanding our view of the cosmos. Ancient photons that have been traveling through space for over 13 billion years will continue to arrive, showing us galaxies that formed shortly after the Big Bang. But simultaneously, galaxies that are currently visible will accelerate beyond our cosmic event horizon, crossing a boundary beyond which their current state becomes forever unknowable to us. We'll continue to see the ancient light they emitted in the past, but we'll never see their future evolution. Trillions of years from now, if observers exist in our galaxy at that time, they'll see a very different universe. A small collection of gravitationally bound galaxies in our local group, surrounded by an increasingly empty void as everything else has accelerated beyond the cosmic event horizon. The cosmic microwave background will have redshifted to such low energies that it becomes undetectable. Future cosmologists would have difficulty reconstructing the Big Bang theory, or even knowing that the universe is expanding, because the expansion would only be apparent in regions causally disconnected from them. This raises a disturbing epistemological question. Are we currently in an analogous situation? Might there be features of the universe, evidence for its origin or structure, that were visible to observers in the past, but which have now redshifted beyond our detection or accelerated beyond our horizon? The answer is almost certainly yes. The universe is much older than the few billion years during which complex structures like galaxies and stars have existed, and even older than the several 100 million years since the first stars formed light from the earliest moments after the Big Bang, from the era before the cosmic microwave background was emitted, is forever lost to us because the universe was opaque to photons. During that time, neutrinos and gravitational waves from those early moments might carry information, but detecting such primordial radiation is extraordinarily difficult and may be impossible with any foreseeable technology. There may have been features imprinted on space during inflation that have expanded to scales far larger than our observable universe, leaving us with only a tiny, unrepresentative sample from which to infer the whole. We may be like cartographers trying to map the entire Earth while being confined to a single small island, using only the geography of that island to guess at the continents and oceans beyond. The concept of causal structure provides yet another way of understanding cosmic boundaries. In general relativity, spacetime is organized by light cones, which define the causal relationships between events. Any event in spacetime has a past light cone, consisting of all events that could have influenced it, sending signals at or below light speed that reach the event in question. It also has a future light cone consisting of all events it could potentially influence. For any observer at any moment, the observable universe consists of the intersection between their past light cone and a spatial slice of the universe. At that moment, the cosmic horizon is where that past light cone intersects the Big Bang singularity. Events outside this light cone could not have influenced the observer, nor could the observer have knowledge of them through any chain of causal connection. This creates a fundamental boundary in space-time, not in space alone or time alone, but in the four-dimensional structure that combines them. The universe might be infinite in spatial extent, but each observer is causally connected to only a finite region of it. Moreover, with accelerating expansion, an observer's future light cone encompasses a limited region, defining not just what they can know, but what they can ever influence or interact with. These causal boundaries are more fundamental than spatial boundaries because they are defined by the structure of space-time itself, by the invariant relationship between cause and effect that underlies all physical processes. Quantum field theory in curved space-time adds another layer of complexity to our understanding of cosmic boundaries and horizons. When quantum fields, which are the fundamental entities describing particles and forces in modern physics, exist in curved or expanding spacetime, they behave in surprising ways. One of the most remarkable predictions is the Unruh effect, where an accelerating observer detects particles in what an inertial observer perceives as empty vacuum. Similarly, Hawking radiation arises from quantum effects near black hole event horizons. causing black holes to slowly evaporate. An analogous effect occurs at cosmic horizons. The accelerating expansion that creates our cosmic event horizon should produce a faint thermal radiation, sometimes called de Sitter radiation, though it's far too weak to detect with current technology. These quantum effects suggest that horizons are not merely passive boundaries, but active physical structures where the quantum vacuum behaves in interesting ways. The cosmic event horizon has a temperature associated with it, incredibly low but non-zero, and it has an entropy proportional to its area measured in Planck units. This entropy represents the information content of the horizon, the number of distinct quantum states that are consistent with an observer being on the inside of the horizon. As the universe expands and the horizon grows, this entropy increases, consistent with the second law of thermodynamics. The horizon itself seems to be a thermodynamic entity, a place where the abstract concepts of information theory meet the concrete physics of spacetime geometry. The landscape of string theory, if it exists, provides perhaps the most elaborate framework for understanding how our universe with its specific properties fits into a larger context. String theory, the leading candidate for a quantum theory of gravity, suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings, and it requires additional spatial dimensions beyond the three we observe. These extra dimensions must be curled up or compactified at scales far too small to detect directly. The number of ways to compactify these extra dimensions, combined with the ways that various fields and branes in string theory can be configured, leads to an enormous landscape of possible vacuum states, each corresponding to a universe with different physical properties. Current estimates suggest this landscape might contain 10 to the power of 500 or more distinct possibilities, each representing a different way the fundamental theory could manifest at low energies. In the eternal inflation picture combined with string theory, different bubbles in the multiverse would correspond to different points in this landscape, exploring the vast space of physical possibilities. Our bubble universe, with its specific values of physical constants and its particular particles and forces, represents just one point in this landscape. The boundaries between bubbles become transitions between different vacuum states in string theory, places where the compactification geometry or field configurations change, altering the effective physics that emerges. This landscape picture raises profound questions about predictability and scientific methodology. If the multiverse samples all or most of the string landscape, producing bubbles with every possible combination of physical laws, then explaining why our universe has the specific properties it does becomes an anthropic question rather than a predictive one. We find ourselves in a bubble with these properties because we couldn't exist in bubbles with most other properties. Stars wouldn't form, atoms wouldn't be stable, complexity couldn't arise. This is scientifically unsatisfying to some physicists because it seems to give up on the goal of predicting the universe's properties from first principles. Others argue that it's simply the correct answer, that the universe doesn't have to be unique or predictable, that the apparent fine-tuning of physical constants finds its natural explanation in the existence of a vast ensemble where all possibilities are realized. The debate touches on the philosophy of science itself, on what constitutes a legitimate scientific explanation, and on whether we should expect physics to ultimately explain why the universe has the specific properties we observe, or merely provide a framework in which those properties are possible. Consider the implications of all this for the ultimate fate of observers and civilizations in an expanding universe with boundaries created by dark energy. As galaxies accelerate beyond the cosmic event horizon, they don't disappear suddenly, but rather redshift to longer and longer wavelengths over time, asymptotically approaching invisibility. A sufficiently advanced civilization, if any exist and persist, might attempt to map the universe while they still can, recognizing that their window of opportunity to observe the cosmos beyond their local group is limited to the current cosmological era. They might try to send probes or messages to other galaxies, recognizing that once those galaxies cross the event horizon, communication becomes impossible. Some cosmologists have speculated about whether advanced civilizations might attempt to escape the heat death or horizon problem through exotic physics, perhaps creating stable wormholes to connect distant regions of space, or even finding ways to tunnel to younger bubble universes in the multiverse. While such speculations venture far beyond current physics into the realm of imaginative extrapolation, they illustrate how cosmic boundaries and the infinite expanse beyond impose ultimate limits on what any civilization, no matter how advanced, could achieve or know. The psychological and philosophical impact of these cosmological discoveries on humanity's self-perception deserves consideration. Throughout history, every advance in our understanding of the cosmos has displaced humans from the center of the universe. We've learned that Earth is not the center of the solar system, that the Sun is an ordinary star among billions in our galaxy, that our galaxy is ordinary among billions of galaxies in the observable universe. Now we're learning that even our observable universe might be just one bubble in an infinite multiverse, and that most of reality lies forever beyond our ability to observe or interact with it. This radical decentering could be viewed as diminishing human significance, but it might equally be seen as highlighting the extraordinary improbability and, thus, preciousness of our existence. If the universe is infinite, or if the multiverse contains infinite bubble universes, then consciousness and intelligence like ours, while perhaps common in absolute terms given infinite space, might still be extraordinarily rare per unit volume, separated by vast distances and multiple horizons. We might be isolated islands of awareness in an ocean of unconscious matter and energy, unable to communicate with other such islands because cosmic expansion and causality impose insurmountable barriers. The mystery of why there is something rather than nothing finds new dimensions when considered in the context of cosmic boundaries and infinity. If the universe is infinite in extent, then avoiding nothingness requires not just the existence of something at one location, but the existence of an infinite amount of something spread across endless space. If the multiverse is real and infinite, then existence is not just actual, but infinitely actual, with reality manifesting in endless variations across countless bubbles. Some physicists and philosophers have argued that existence is in some sense easier or more natural than non-existence, that nothingness is actually impossible or unstable, that quantum fluctuations inevitably produce something from nothing, and that once existence appears anywhere, it propagates through inflation to fill infinite space. This inversion of the traditional puzzle, where the question becomes not why there is something rather than nothing, but why there would ever be nothing when something seems inevitable, represents a radical shift in perspective. The boundaries and horizons we've discussed become features that organize this infinite existence into structured regions, creating pockets of order and causality within an otherwise unbounded reality. The role of symmetry and symmetry breaking in defining cosmic structure provides another technical but important perspective. The laws of physics at fundamental levels often exhibit symmetries, transformations that leave the laws unchanged. The early universe, in its hot, dense state, likely exhibited high levels of symmetry, with fundamental forces unified and particles indistinguishable in their properties. As the universe expanded and cooled, These symmetries were spontaneously broken, differentiating the forces and giving particles their distinct properties. These symmetry-breaking transitions occurred at different times and temperatures as the universe cooled. First grand unification symmetry, breaking at incredibly high energies shortly after the Big Bang. Then, electroweak symmetry breaking about a trillionth of a second later. And finally, quark confinement forming protons and neutrons. Each transition represented a kind of boundary in the universe's history, a moment when the nature of matter and forces changed discontinuously. In eternal inflation, different bubbles might undergo these symmetry-breaking transitions differently, with symmetries breaking in different patterns, leading to different forces and particles dominating in each bubble. The boundaries between bubbles thus represent not just spatial edges, but transitions between different symmetry-breaking patterns, different solutions to the fundamental equations that govern reality at the highest energies. Returning to the question posed at the beginning, we can now appreciate its full depth and subtlety. Can the universe be infinite and still have an edge? The answer is emphatically yes, but with crucial qualifications about what we mean by infinite, edge, and even universe. The cosmos exhibits both infinite and bounded characteristics simultaneously along different dimensions and from different perspectives. It is potentially infinite in spatial extent, yet bounded by horizons beyond which we cannot see or reach. It may be infinite in duration, at least toward the future, yet bounded by temporal edges at the Big Bang. And the heat death. Each bubble in the multiverse may be finite with clear boundaries, while the multiverse ensemble is infinite. Space may be infinite in extent, yet bounded by discrete Planck scale units that prevent true continuity. The observable universe has an edge defined by the speed of light and the age of the cosmos, while the unobservable universe may extend without limit. Causality creates boundaries in spacetime that divide the cosmos into regions that can and cannot influence each other, even if space itself is endless. These multiple meanings of infinity and boundaries reflect the richness and complexity of the cosmos we inhabit. The universe refuses to fit into simple categories, instead manifesting as a multi-layered reality where different descriptions apply at different scales and from different perspectives. The mathematical infinity of endless space coexists with the physical finitude of the observable universe. The boundless expansion into the future coexists with the boundary conditions set by the Big Bang in the past. The infinite possibilities explored by the multiverse coexist with the specific, finite reality we observe locally. This multiplicity is not a defect in our understanding, but rather reveals the sophisticated structure of existence itself, a structure that transcends the simple dichotomies of infinite versus finite, bounded versus unbounded. For observers confined to a single location in space and time, moving forward through the cosmos at the inexorable rate of 1 second per second, these boundaries and infinities define what we can know, what we can reach, and what must remain forever mysterious. We live in an extraordinary era where we can observe the cosmic microwave background, map the large-scale structure of the universe, detect gravitational waves from colliding black holes, and construct theoretical frameworks that extend far beyond what we can directly observe. Yet, we also recognize the fundamental limits imposed by the finite speed of light, the accelerating expansion of space, and the quantum nature of reality at the smallest scales. These limits create boundaries to knowledge that no amount of technological advancement can overcome, short of discoveries that would revolutionize physics itself. The universe at its largest scales exhibits a structure of breathtaking elegance. Galaxies, grouped into clusters, clusters connected by filaments of dark matter and visible galaxies. Enormous voids between these structures, all expanding according to the Hubble flow, while local gravitational binding preserves structures at smaller scales. This cosmic web extends as far as we can see, showing the same statistical properties in all directions, suggesting homogeneity and isotropy at the largest scales. If the universe is infinite, this web extends forever, an endless tapestry of structure created by gravitational instability, amplifying quantum fluctuations from the inflationary era. If the universe is finite, the web eventually closes back on itself, creating a finite but unbounded topology where space curves through higher dimensions we cannot perceive. Either way, we observe only a tiny fraction, a single bubble of visibility in what may be an infinite expanse. The questions we've explored here sit at the frontier of human knowledge, in territory where physics meets philosophy, where observation meets speculation, where what we can know confronts what we might never know. These are questions that our descendants, if any exist in the distant future, might have better answers to, armed with centuries or millennia of additional observations and theoretical development. Or these might be questions that can never be fully resolved, not due to limitations of human intelligence or ingenuity, but due to fundamental constraints imposed by the structure of space-time itself. The edge of the universe, if it exists, might be forever beyond reach, not just practically, but in principle, hidden behind horizons that no observation can penetrate. Yet the search for answers drives us forward. Every telescope we build, every satellite we launch, every theoretical framework we develop brings us closer to understanding the cosmos we inhabit. We are creatures of finite understanding, contemplating the infinite, beings confined to a tiny corner of reality, attempting to grasp the whole, observers bound by the speed of light and the expansion of space, trying to perceive the totality, that we can even formulate these questions, that we can construct mathematical theories describing infinities and boundaries, that we can gather observational evidence constraining the possibilities, represents an extraordinary achievement of the human mind. We may never know with certainty whether the universe is infinite or bounded, whether we live in one bubble among many or in a unique cosmos, whether space continues forever or curves back on itself beyond our horizon. But in the attempting to answer these questions, in the exploration of the concepts and mathematics needed to even formulate them properly, we expand the boundaries of knowledge and push back against the darkness of ignorance, claiming a deeper understanding of the reality we inhabit. The universe, in all its mysterious grandeur, remains our home and our challenge, inviting us to observe more carefully, to think more deeply, to imagine more boldly. Whether infinite or bounded, whether one among many or uniquely existing, whether extending forever or curving back on itself, it provides an endless source of wonder and questioning. The paradox with which we began, how something can be infinite yet have an edge, resolves not into a simple answer, but into a rich tapestry of possibilities, each revealing different aspects of cosmic structure, each suggesting different futures for cosmological investigation. In this sense, the question itself was always more valuable than any particular answer, because it leads us into the deepest mysteries of existence, forcing us to confront the limits of knowledge while simultaneously pushing those limits ever outward, reaching toward the infinite, even while acknowledging the boundaries that constrain us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.